All right, let's get into it. When we think about oil, we kind of picture those old-timey gushers, right? Just shooting straight out of the ground. But the truth is, getting oil out of a reservoir is a massive science and engineering challenge. See, most of it desperately wants to stay put.
So let me ask you something right off the bat. Imagine a brand new well, drilled into a reservoir that's just brimming with natural pressure. What percentage of the total oil in there do you think comes out on its own, just from that initial push?
The answer is, well, it's shockingly low. We're talking only about 10 to 15%. That's it. All that work, all that drilling, and we've barely even scratched the surface.
Yeah, you heard that right. This means that after that initial natural pressure dies down, a staggering 85 to 90% of the oil is still down there, trapped in the tiny little pores of the rock. And that is the fundamental problem that has kept engineers busy for decades.
So how do we get more? Well, you have to tackle this in stages. Let's first take a look at the conventional playbook, for getting what's often called the easy oil.
So the process starts out pretty simply. Primary recovery is basically just opening the tap and letting the reservoir's natural pressure do all the work. But once that fizzles out, we move on to secondary recovery. And this is an active process. Almost always it means water flooding. You're literally pumping huge amounts of water down injection wells to physically sweep more oil toward the wells that are producing.
But here's the thing, even after all that effort, after both primary and secondary recovery, we're still only getting an average of about 35% of the oil. That means nearly 2/3 of the oil that was originally there is still in the ground. That's just a huge amount of stranded energy.
This is where the really cool science comes into play. To get the rest of it, we have to move beyond just pushing the oil. We have to start changing its properties on a molecular level. And this is called enhanced oil recovery, or EOR for short.
So the crucial point here is that EOR isn't about pushing harder. No, it's about using these advanced techniques, think heat, chemicals, specialized gases, to fundamentally alter the physics and chemistry down in the reservoir and basically convince that stubborn, trapped oil to finally start flowing. And the potential payoff is absolutely huge. Just look at the jump on this chart. EOR methods can boost the total recovery from that 35% average all the way up to 60%, sometimes even more. We're talking about potentially doubling the output from an existing field without drilling a single new well. So let's open up the EOR toolkit, see how this stuff actually works. Because it's not a one-size-fits-all solution. Oh, no. Engineers have a whole toolbox of methods they can pull from, depending on the specific geology and the type of oil they're dealing with. At a high level, these methods fall into three main buckets. You can heat the oil up to make it flow better, you can mix it with gases to change how it behaves, or you can essentially wash it right out of the rock with some pretty specialized chemical cocktails.
Okay, first up, and the most common EOR method is thermal recovery. This is the go-to technique for reservoirs with really heavy, thick oil. We're talking stuff that's more like molasses than what you put in your car. The goal is simple: heat it up to lower its viscosity, which is just a fancy way of saying make it thinner and less resistant to flowing. A classic example of this is a process with a fantastic name: huff and puff. It's just what it sounds like. First, you huff by injecting high-pressure steam down a well. Then you let it soak for a while, allowing all that heat to spread out and thin the oil. And finally, you puff by reopening that same well and producing the heated, much easier flowing oil. Next up in the toolkit is gas flooding. Now, this is where we inject gases, often it's carbon dioxide or nitrogen, into the reservoir to interact directly with the oil itself. The key scientific principle here is something called miscible displacement. Now, miscible just means that the gas can completely dissolve into the oil, kind of like how sugar dissolves in your coffee. When this mixing happens, it gets rid of the forces that hold little oil droplets in place, which effectively frees them from the rock pores. And a really clever way they apply this is with the water alternating gas process, or WAG. See, instead of just pumping in gas, which might find an easy path and bypass a lot of oil, you alternate. You inject a slug of water to control the flow, then a slug of gas to mobilize the oil, then water again, and so on. This cycle gives engineers much better control and leads to a way more efficient sweep of the reservoir. The final category in our toolkit is chemical flooding. So if thermal is about heat and gas is about mixing, then chemical flooding is all about washing the oil out of the rock, using these incredibly sophisticated, custom-designed chemical solutions. And I love this analogy from the source material because it just makes the whole concept click
instantly. One of the key chemicals they use is called a surfactant, and it works exactly like your dish soap. It breaks the surface tension that glues oil to the rock, letting the water scrub it clean and carry it away. It's that simple.
So besides surfactants, which reduce those sticky forces that glue oil inside the rock, engineers also use polymers. These are long-chain molecules that you add to the injection water to make it thicker, creating this thick soup. This thickened water is way better at pushing the bank of oil without just finding a little channel and sneaking through it. And sometimes they use a powerful cocktail called ASP, which combines alkaline chemicals, surfactants, and polymers for a maximum 1-2-3 punch.
Okay, so you can see this is some seriously powerful technology, but its impact doesn't stop at the wellhead. Let's zoom out and look at the bigger picture and what the future holds for these techniques. So here's a really fascinating twist. When CO2 is used for gas flooding, a huge amount of it never comes back up. It actually stays permanently trapped or sequestered deep in the underground reservoir. And this has turned some EOR projects into a really effective form of carbon capture and storage. But look, EOR isn't a silver bullet. For one, it's incredibly expensive, so whether or not it's used often just depends on high oil prices to make sense economically. There are also environmental risks that come with handling such large volumes of chemicals. And while it's pretty common onshore, trying to apply these complex techniques in deep-water offshore fields, well, that's a whole new frontier that we're still just beginning to explore. So let's wrap this all up. I think the key takeaway here is that what was once considered waste, that vast majority of oil just left in the ground, is now being unlocked through some truly remarkable scientific ingenuity. We are literally learning how to squeeze more energy from a stone. And that leaves us with a final thought, right? This whole field is about turning a problem of inefficiency into a huge opportunity for innovation. So as we get better and better at this, it really makes you wonder, what other resources, the ones we've currently written off as unreachable or unrecoverable, are just out there, waiting for the right technology to come along?